This is yet another lecture about multiple regression model. This time we think about the following problem. We are given a huge number of potential independent variables. We want to choose from this huge set of variables a smaller subset in such a way that our prediction for the dependent variable is efficient in a sense that we have high R-square value and we have relatively small number of independent variables in such a way our model is relatively simple. There are several procedures to choose a good subset of independent variables. We start with discussing the model which is called all regressions model. All regressions means that essentially we should calculate R-square for all possible subsets of independent variable in our all possible subsets of independent variables that are in our disposal. This means that we have to really produce and analyze a huge number of numbers. We will not be doing that exactly, but we will at least start in this direction. So the procedure is as follows. We start with the linear regression with only one variable, independent variable. We look what happens, then we increase the number of independent variables by one, then again we look what happens, and so on up to the end. And then seeing how things proceed, we make our decision based on values of R-square we see. Probably the easiest way to explain this all will be to work on concrete example. Let me then introduce the data we are at our disposal. The data contains public health information about countries, 134 of them from year 2015. The data are the following. Our dependent variable will be life expectancy in years for each country. And we would like to predict this number based on several potential dependent variables. We have 17 of them. This is a big number of variables. And the variables are the following. The variable number 2, distinguish between developed and developing countries. Variable number 3 is about adult mortality. This variable says how many deaths in people between 15 and 60 years old are during 1 year in a country per 1,000 people of the population. Then variable number 4, number of infant deaths per 1,000 people. Then alcohol consumption. It is calculated in liters of pure alcohol and expressed per person. Then the percentage of 1 year old which are immunized against hepatitis B. Variable number 7, number of measles cases per 100 persons. Variable number 8, average body mass index of the population. Variable number 9, number of deaths among children under 5 years old, again per year and per 1,000 people. Variable number 10, the percentage of 1-year-olds that are immunized against polio. Variable number 11, the expenditure on health in percentage of the total government expenditure. Variable number 12, the percentage of 1-year-olds that are immunized against diphtheria, pertussis, and whatever, DTP3 immunization. Variable number 13, this is deaths of children under 4 years old related to HIV virus. This is calculated per 1,000 live births. Variable number 14, gross product of the country expressed in USD dollars. Then variable number 15, prevalence of thinness in age in children of age from 10 to 19. So it says what percentage of young people are thin. 16, the same, but in children between 5 and 9 years old. Then variable 17, it is human development index. I don't really know precisely how it is constructed. It takes value from 0 to 1, but as we will see later, it is highly correlated with variable number 18, which says how, on average, how many years of schooling a person receives in each country. So as you can see, there are very different variables, some related to immunization, some related to economic questions, some related to, say, lifestyle, like BMI or alcohol consumption. And our goal is to choose among those 17 variables the smaller subset that is good enough to predict life expectancy. Okay, so first of all, let us look at our dependent variable. Here is the appropriate histogram. No, it isn't exactly symmetrical, but we can, I think, visually reasonably assume that it is close to normal. Here I have checked that I really do have 134 countries. And what we see here is the correlation matrix of all the variables. So all the 18 variables. Of course, the first variable is our dependent variable. The rest of them are independent variables. The picture here is the so-called heat map. So it contains not only numbers, which are correlation coefficients between variables, but also it is those numbers are color coded, and we can easily see which variables are correlated strongly correlated between themselves. Of course, between the first variable and the rest, but also between themselves. So as when we look at the first row here, we see several variables that can be of use. For example, there is definitely variable number 3, which is negatively but strongly correlated with our dependent variable. There is also variable number 5, which is strongly correlated. Variable number 8. There is also variable number 13. And the last two variables, variable number 17, which is this human development index, and variable number 18, which is years of schooling. So there is quite a good source of information, at least on the first glance. Then we look at the whole table, and here we see some pairs or even bigger subsets of variables that are correlated between themselves. Now, definitely, there is some rounding here. So this one, it isn't probably really exact one as on the diagonal, but something close to one. But it seems that variable number 9 is very strongly correlated with the variable number 4. Therefore, we definitely will not use both of them in our model, because this will cause the model to crash. In the formulae that we derived in previous lectures, we've seen that there appears the determinant of the covariance matrix. So if we use among our independent variables that have correlation 1, then this big determinant of the covariant matrix will be 0. So it will not work. We have to choose one of the variables 4 or 9, and we usually choose the one which is stronger correlated with the dependent variable. So in our case, it will be definitely from those two, it will be a variable number 9. We also have here strong correlation between 9 and 7, and the same between 7 and 4. So probably this subset of highly correlated variables is not just 4, 9, but 4, 7, 9. And from these we will use, again, I suppose 9, because it is the correlation is stronger between 9 and 1 than between 7 and 1 and 4 and 1. Another subset of correlated variables will be 12 correlated with 6. So again, 12 or 6, and when we look at correlation with the first variable, it will be rather 12, because it's higher. Another subset of correlated variables, we can see here 12 and 10. So again, there will be 3 of them because again 10 and 6 10 and 6, yes, 10 and 6 are also strongly correlated. So there will be 6, 10 and 12, the subset from which we take 10 or 12, because here we have the same number. And another subset of still two subsets, 15 and 16. Those two variables were both about thinness. The first one about thinness in young people, and this 16 about thinness among children. So we choose one of them. And also another subset, 17, 18, human development index and years of schooling. They are very strongly correlated. Therefore, it is again enough to use one of them. So I have summarized it all here. So we have the following subsets of correlated variables: 9, 7, and 4, from which we choose 9, 6, 10, and 12, from which we choose 12, 15, 16, from which we choose 16, and 17 and 18, from which we choose 17. And we add the rest of variables which are not strongly correlated to anything, not strongly correlated between themselves. This means that we obtain 11 potential independent variables to use in our model. This is, of course, quite a big number. Then to see if our if it is really linear model that we should use here, we look at the scatter plot of the dependent variable by at least some of the potential independent variables. Probably we should do it for all of them. However, this will take time, so let us look only on some that later on appear to be important. So this is the scatter plot of life expectancy by years of schooling, which will be very similar to the picture of life expectancy by Human Development Index. But since life expectancy is in integer, but since years of schooling is in integer numbers, so then this plot is probably more easy to analyze, and we see that the dependence is more or less linear. So okay, nothing wrong happens. Then there is the scatter plot of life expectancy by years of by number of deaths of children under 5 years old. That death relates deaths related to HIV, and I see that I've mixed up something. There shouldn't be life expectancy by HIV related deaths. Oh, it will be like that. So this is not that linear. We can see here some like 1 over x or something. But still, those points here are there is a small number of exceptional countries, like 3 of them, and in the bulk here we have more or less linear dependence. However, we see that there is a huge number of countries, fortunately, a huge number of countries when there is just no deaths of children under 5 years old, deaths related to HIV. And there is a scatter plot of life expectancy by adult mortality. And what we see here is quite interesting. There is a group of countries in which this dependence is definitely linear. And there is another smaller group of countries in which this dependence is also linear but different. So if we were to use this this variable number 3, which is adult mortality, we should probably look for the interaction with the other variable, or just so if we look for the interaction, it means that we in fact calculate model in subgroups, because we see here that this is here we will have a very different linear regression between those two variables than in this group. However, for this procedure, we disregard this. This is an important matter. If we really want to know what happens, we should go into the details, but for now we disregard it and we proceed to choosing variables for our regression model. So we start with building regressions between just 2 variables, one dependent and one independent. And what I have calculated here are R squares for all pairs, variable 1 as dependent and all of the other variables chosen before, so this 11 interesting variables chosen before as independent variables. And what we can see here, we see that what I've marked, oh, this is probably wrong. No, it isn't. So first of all, I marked those variable in red, those variables that have r square over 1/2. And also I added in orange those variables that have r squared over 0.2. You can see that the most valuable variable is variable 17, which is Human Development Index. But there are also other important, there is adult mortality, there is this 13 variable that I forgot what it is. And let us check what's 13, variable number 13. HIV related deaths. So this is also quite important variable. And there are some of them which are less important but also may add some valuable information. So I keep it in mind. I'm in the set that I have selected 3, 13 and 17, and also I remember the other 5, 8 and 14, 16 just for backup. Then I proceed to the regression with 2 independent variables. And now let's see how long is the table. Yeah, so when we, of course, it's clear that when I choose one among 11 variables, I got 11 results. When I choose 2 among 11 variables, I have 11 times 10, I have very long list. Nevertheless, we will try to analyze this. Again, I marked in red those rows that correspond to r squared over 1/2. And what we see that whenever variable 17 appears or variable 3 appears, I get quite high number. Also, the pair 5, 13, no, here is 17, 8, 13, so again variable 13. When variable 13 appears, I also get quite high number. And what we see here, 17, or 13, 16, yeah, so these are, everything happens among the variables that we have already chosen. The best pair is 13 and 17, and here I have already r squared equal to a little bit over 0.8. So this is quite good prediction. We see that this list is very, very long. When we add the third variable, it will be even longer. The length of the list will increase up until I have 11 variables. That means that it will increase up until I get 5 variables. Yes, but then for the 6 will be the same, and then the number will start decreasing. So we will definitely not want to go into looking at such a big table for 3 variables. Therefore, at this point, I decided to restrict myself to the variables that appear in those red rows, and I see that definitely variables 3, 13, 17 are the most valuable, but also variables 5, 8, 14, 16 appear here. Those other 5, 8, 14, 16 do not appear alone, but always accompanied by at least one of those. But so what I'm going to check is whether using one of them will really help in predicting based on 3, 15 and 17. So this is what I suppose will be happening. But before that, we do regression with 3 independent variables. What I really expect is that this will be the best set at this stage of the selection process. So let us see. So now this table is not that big because I restricted. I have chosen only 7 from previously 11 variables, and I have three independent variables in my regression model. And again, we see that definitely 3, 13, 17, this is the best set. And adding some others, definitely adding 5 may help a little bit. Maybe adding 16 or 14 may help a little bit. But the differences here start to not to be very big. As you can see, I have marked here only results over 0.8. It seems that this stabilizes on the set 3, 13, 17. However, we might check whether adding some variable from the other 5, 8, 14, 16 if it helps. So we proceed to analyzing regressions with 4 and 5 independent variables. 4 independent variables, again, the table with more or less the same length. As we expected, there are more red rows because adding every variable may only increase the quality of prediction. However, it may increase only slightly. And what we see is precisely that. So we have 3, 13, 16, and 17. So this is our previous best set with 16 added, and what we get is 0.86 as compared to 0.58. 0.858. So the difference is on these decimals. Yes, so this is rather small. However, no, there are also other possibilities, but this is the best. And then we proceed to 5 independent variables, and we see that again 3, 15, and 17 with some additions. Which one is the best? This one is the best. I can make it bigger as previously. This one is the best, but again the difference is very, very small. So now we face the following decision. If we want to have a more complicated model involving, for example, 5 or 4 independent variables, or we want to have simple model with only 3 independent variables, but a little bit lower R squared. This a little bit lower it means on the 3rd position after the comma, so it is not really much. And my decision at this point will be to choose this multiple regression model with 3 independent variables. These independent variables will be adult mortality, HIV-related deaths of infants, and human development index. And this gives us R square over 0.8, which means that when we predict life expectancy using these 2 variables, we make on average the error of 85% less that if we just predict based on the mean value of life expectancy. So this is quite efficient prediction. And the model is simple. So we have only 3 variables that we have to know before we make our prediction. Let us also look at the errors of prediction. Maybe I will make it a little bit bigger and more visible. The errors, because you have seen during the computer lab that the previous data set about wine quality was probably not the best data set chosen for multiple regression, because definitely errors did not follow normal distribution. So to be on the safe side, I have checked here. Here we have a histogram of errors of prediction in our model, and this is reasonably normal. Therefore, we may assume that assumption about our data set are fulfilled. Assumption for building multiple regression model are reasonably fulfilled. And we have quite a good model with 3 independent variable and R² over 85%. Thank you very much. This is all for now.